Right, so here we're going to do the second part of 1.2.1, and we're going to go through these sections here. So let's go. So obviously, if a CPU is going to simulate multitasking, it's going to look like it's doing more than one thing at once, you're going to have to think about how you schedule the instructions. Like, how do you allocate time out for all of the different jobs that you need to do? So scheduling is there to improve the response time to the user, right? To maximize all the CPU time, to ensure fairness in a multi-user system. So if you've got 7 users using the same computer, it will enable that you can give everyone a fair chance to use the programs. And it enables multiple programs to run at once efficiently. So let's look at the different scheduling options. To me, the most obvious one is something called a round robin. Essentially, you set an amount of time that you're going to give to each process, and it's the same for each one. So let's say they're going to give 1 second. Obviously, it's not 1 second, but let's say 1 second. So it spends 1 second on process A, 1 second on B, 1 second on C. If A was to finish, say, half a second in, then it would immediately go on to the next process. Obviously, it's not going to sit there and wait doing nothing. So basically, if it isn't finished in the 1 second time slot, then it will go on to the next process and it'll have to wait its turn again in a big long list. And it says it's first in, first out, because basically the first one that comes in gets executed first, the second one third. But they still only get equal amount of time. So that's quite a simple, obvious solution, and quite a popular one, really, obviously. But the other one is something called first come, first served, which is basically each process is done in the order they come in. So if A comes in, it is executed until completion, and then the processor moves on to task B. So obviously, this means you might have to wait ages if you're here for your task to complete if A and B are long. And this sort of kind of stops, really. I mean, not completely stops, because it can do one job, then another, then another. But it stops any real idea of multitasking, because kind of you're not really doing a little bit of each. You're literally doing one job till it finishes. So yeah, so that's first come, first served. Then we've got something called a multi-level feedback queue. So at this point, I'm going to pause talking about scheduling and focus on what a queue is. Because just like before, if you watched my previous videos, we had to discuss what a stack is. Well, a queue is very similar to a stack, except that, it works in the same way you join a queue in real life, in that you join at the end and you come out of the front. Whereas a stack, you join at the front and come out of the front. So, so a queue is different. Okay, so here we've got the example of my rubbish queue program. So you can obviously add things to the queue by unqueuing them. So 23, 45, 9, and then look at the queue. And then you've obviously got 9 just joined at the back of the queue. 23 is at the front. And obviously if we dequeue, it's going to give us 23 as we got there. And then we can print the queue again. You'll still see it's 9 and 45. So you add at the back, take out the front, just like a normal queue. And that's an example of what a queue looks like. So now we know what a queue is as a data structure. Okay. Now we're going to look at multi-level feedback queues. So the thing with a multi-level feedback queue is that the processes have different queues. Okay. It depends on how many the algorithm dictates in the scheduling. But remember, a scheduling process is here. So remember, if we go back, we're not talking about data structures like we were before. Now we're just talking about scheduling processes. So here I've got 4 processes. Now there's 3 queues in my system, but there could be as many as they want with different priority levels. Okay. So I'm going to say that we add 3. Now, as it's a queue, okay, things will get executed. I'll talk about that in a second. Let's say I want to very quickly add 2 processes to the list, A and then B, and they're both medium. So A gets added and it goes there, and then B would get added behind it and A would shuffle forward, and we've got our queue with A followed by B. Okay. Now what's going to happen is, it will go through the queues, executing all of the high ones first in a front to back order. So this way. Then it will execute all these ones this way, and then if there's anything left, it'll execute these. So it will not execute anything in medium level in this version if there's anything in high. So let's say D was added to high, and then C was added to high, right? So now we've got it in that order. Now it's going to execute D first, then C, then A, then B. And that's basically how a multi-level feedback queue system works. And there's nothing too crazy about it. Let's go here. So there are multiple queues with different priorities. If a process uses too much CPU though, it can be moved to a lower priority queue. So this is the clever bit, or the bit that makes it more interesting. So let's just say we've got this process here like this. Let's say this has been waiting so long that it's never getting executed because there's constantly things being put in high and medium. What the algorithm will do is it will move it up to a higher priority queue. Now, how and when it does that is up to the algorithm, and that'll be different on every single design. This is an ideology, we're not giving you specifics. So things can move up the queue, okay, if it's waiting too long, which is called starvation. We've talked about that before, but we'll talk about it again in a minute. So basically, if it's been starved of CPU power, it can be moved up. If it is taking up too much CPU power, like it's being executed too often, maybe it can be moved down. So things can move up and down the priority queue, thus enabling them to more likely to be done. So it doesn't mean just because you're in the bottom here that you're always going to be stuck there because higher priority things come along, because you will eventually move up in priority. Obviously, you would go to the back because that's how the system works. It's a queue, but you'd still be in the queue, and this might be executed and just taking too long. It might be dropped, and now this gets done, and now you're being executed. So that's how multi-level queue system works. Okay? So there we go. We are now on shortest job first. Okay, so this is I'm not going anything really interesting with this one because it's quite an easy one. So the user, this is the key thing with this. There's two that are very similar sounding. The user estimates the execution time, and the job with the shortest execution time is executed after the current one finishes. I suppose I could borrow this for a minute and move these out of the way to vaguely demonstrate that. So let's say this is being, actually I could do this live, yeah. Let's say I've got, this is going to take 5, seconds we'll say, but obviously that's not really how it would be done in cycles. But let's just pretend this is going to take 5, this is going to take 6, it's going to take 2, and that one's being executed, and we don't care how long it was, because once they're being executed, they will be done until completion. Okay, it's only when they're finished, so that one finishes, bye-bye, and then it will look to see which one has the shortest one, and that will go on next, and then obviously that's going to go away, and then that gets completed, and then it would of course do B, and then that gets completed, and then it would of course do A, because that's the only one left. But what can happen is, right, let's get some of the numbers back up actually because we're lazy. Where's 2 gone? There we go. So A could, let's say C finishes, B finishes. Just when B's about to finish, you think, yes, A's turn, another one comes in. So then B, so A, and then D's getting done. When G's about to finish, oh, and A just never gets done because you get starved of CPU attention because it has a higher waiting time and execution time, and that can happen, and it's quite annoying. So that's a problem with shortest job first. But this often gets confused with shortest remaining time, good spelling there, where this is when a new job comes in, the time of completed will be estimated. So before the user said how long it was going to take, now it's estimated with some sort of algorithm. Analyze it, check it. That's not the main thing though, but it's only estimated when a new job comes in. So when a new job comes in, right? So these are not existent right now. Let's put them off, right? Actually, let's give them their estimated times of 2, 3, 5, and 6. Okay, but these are not in. Before, those were already in their little list of jobs. Now these are not come in yet. These are not waiting to be executed. So let's go, right, this comes in. Of course, there's nothing at the moment being executed. So of course it gets executed. Then this comes in. Now we look at the shortest job time remaining, okay? And a newer job with a short execution time than the current job will take over. So let's say this has still got 4 to go, okay, because of, it's being executed a little bit. That won't execute, so I'll just go over there waiting its turn. Now 3 comes along, that's immediately, should we say, so there's no time change. Right, now that is less than that. So when a new job comes in, and only when a new one comes in, it's not constantly being checked, like even if, for whatever reason, this one would then take over. This would be paused and this would be executed, okay? And let's say this goes down to 2 or 1 because it's, some of it's done. Then this one comes in and this has got more time than it's left on that one, so that would be finished. And then, of course, that would go on, and these would just wait their turn. With whatever, when that's finished, it will look for the shortest one, similar to the other one. The only main difference is between the two, which is this one and this one, is that when a new job comes in, it can actually overtake it. Whereas with this one, when a new job comes in, it just becomes the next one to be executed. The other one is still finished. But if this one has a less execution time than the other one has remaining, this one will take over. And the other main difference is that with shortest remaining time, the job is estimated with an algorithm rather than the user estimating the execution time. Okay. So that's those ones there. And again, of course, starvation can occur because if you have a high waiting time, you can just be sitting there forever. And in fact, this one occurs even more because as new job comes in, they can actually take over. So it, you know, if loads of little jobs come in, they can just keep taking over. Okay, so now we're looking at operating system types, which is part 5 of this section. So here we're going to look at one called a distributed operating system. And a distributed operating system basically coordinates the processing of a single job or process across multiple computers. This is used heavily in 3D rendering, data analysis, high-level stuff, and in other areas, and we'll talk about as well. And it vastly speeds up processing as resources are shared. So imagine one program like Blender rendering us a video out, and it is rendering it across 10 different computers on a network, okay? And the distributed operating system handles all the sending out of instructions and data. And it's sort of a layer of abstraction because the user here, we're going to hear a lot about abstraction, the user here doesn't need to know what's going on. It just runs the program, presses a button, and then the OS does all the actual work behind the scenes of getting them to render it. So that is a distributed operating system. They're used in many different things. Okay, so now we've got an embedded operating system. So they're used in embedded systems, which are simply a combination of hardware and software designed for a function. So think of a washing machine, tumble dryer, microwave, things like that, alarm clock. So the embedded system might have an operating system. They don't all have one. But if they do, it'll be very different to the one using a desktop. Okay, it will have obviously very minimal features because it's a very small piece of software designed to run on a very low-powered machine. It'll have a very simple user interface, if any major interface at all. It's probably going to be stored on a ROM chip, so it's not going to be like loaded in from secondary storage. It's going to be stored straight on a ROM chip. And of course, it's going to have low resource costs. This operating system is going to use very little memory, processing power, etc., because it's designed for a simple system. So now we're looking at something called a multitasking operating system, which basically we've covered really by looking at scheduling, because obviously we talked about multitasking. But essentially, just so you know, in case it comes up that you didn't really get what it meant, essentially Windows is a multitasking operating system. It allows you to give the impression that you're running more than one task at a time by quickly moving from job to job in varying formats. That's how we did it before. We literally discussed how the CPU might do that or the operating system might do that. Okay, so that's Multitasking OS. I'm not going to dwell on that because, we went through it. So here you've got a MultiUser OS. And this is where one computer, normally a powerful server or mainframe, can allow multiple users to share its processing power. So this is the opposite of this. This is one computer using multiple computers' operating power. One user, lots of computers. This is lots of users, one computer. So in the old days of like when I went to university, in some of the labs there, when you logged into the machine, you weren't actually running Word or whatever on your machine. You were running it on this mainframe here. So the 20 users in the room would all run their sort of computer program on the main server like this. And these were called terminals. And obviously that means that these can be very cheap because they haven't got to have much resources because really they're just running the program that runs the software on the mainframe. To the user, it might look like they're running on their own computer, but actually they're all sharing resources from main computer. Okay, so that's what MultiUser OS is. It allows one computer to be connected to by multiple people and used at the same time. Right, now we're over to real-time operating system, and that is one that's designed to be super fast. It's normally used in digital signal processing, hospital machines, any safety critical environment stuff, and there's anything that needs speed really. The main things to talk about is it must respond extremely quickly to inputs, and that could include a large number of inputs. It will often have a fail-safe in place to detect hardware failure because obviously these things are critical. And often there'll be something called redundancy, which it sounds like it's not the word, doesn't really sound like what it means, but essentially it's having the idea of what happens if something goes wrong. So we might have multiple copies of something in there. So if one sort of like here, this is, by the way, this is a pacemaker for a heart. So if your heart isn't getting the right signals from the brain, or I don't know, I'm not an expert in this, obviously. this will basically shock your heart to pump, really. And I'm assuming that can't go wrong because obviously you would then die. So it probably has fail safes in it. So there's probably 3 or 4 versions of everything in there. Basically, so if one goes wrong, there's others and gives you time to repair. So yeah. So here we're going to look at the last part of the unit, which is BIOS and device drivers and virtual machines. So a BIOS is the basic input-output system. Computers execute code. So when booted, what are they executing? Well, when you turn your computer on, you're basically executing something similar to the BIOS. And its main job is to initialize the hardware, do a little check on it, and then boot your main operating system. It's either stored on an EEPROM or NOR flash memory. And these are essentially read-only, but they can go into a write mode, which allows you to overwrite them. But they have to be erased and then written over, and then they're read-only again. You can't sort of read-write to them back and forth like a secondary storage or main RAM. You either set it to a sort of mode where it has, and it normally has to be written all in one go. Like you have to you have to delete everything off it, right over the top of it, and then you say right done, and then it's now back into a read-only mode. Okay. So yeah, that's what basic input system does. It allows you to sort of set up your computer, and then it boots up, checks the hardware, and boots the OS, Windows or Linux or whatever. So what is a device driver? Well, a device driver is another level of abstraction, okay? So a device driver is a program that interfaces between the operating system and the hardware. And the whole idea behind it is that if you make some new hardware, how is the operating system going to know how to talk to it? Well, you basically write a program in between. So the operating system can talk to this driver and it talks to the hardware. Obviously, the people that make the driver normally made the hardware. Now, device drivers have to be made specific for each OS. So if you made, say, a new graphics card from NVIDIA 6900X or whatever it is out now, and if you're watching this, then there would need to be a driver written for Linux, written for macOS, written for Windows. Normally NVIDIA would make these. Sometimes third parties make them. They're normally not as good because they don't have an understanding of the hardware. Or they might convert a driver for Windows to Linux or something. But anyway, obviously NVIDIA will release one for the graphics cards because they're a big company. So they will release a driver for that exact piece of hardware for that system. So they're specific to the hardware and the operating system. You will sometimes find like Windows and macOS will have generic drivers for things. Like say you get a fancy mouse. Like the main features of the mouse won't work because a generic driver works with them. Or because the company have given Windows the ability to release a driver with them. It might be an older driver because they can't keep updating. But generally, at the end of the day, you need to have a device driver. And the reason I call it an abstraction is because the applications don't need to know how the operating system does it, and the operating system doesn't need to know how the hardware works because they talk to the OS and the OS talks to the device driver. Anyone below only needs to know about, only needs to talk to one level below. So the operating system doesn't need to know at a hardware level how things are working because that's what the device driver does. And the person writing an application doesn't need to know at a device driver or a hardware level how stuff's going on. It just needs to talk to the OS. So that's why it's an abstraction, okay? So last but not least is a virtual machine. A virtual machine is basically any software that allows you to run a copy of another machine on your system. Here I've got an example of Windows running inside Linux. I'm going to show you an example of me running Linux inside Windows. Java is also considered a virtual machine, which we'll look at later. Any console emulator which you've downloaded or used, MAME is the arcade one, Project 64, SNES 9X for various things. They emulate the console. They make a virtual copy of the machine and you run it on yours. So I'm just going to get up my Linux one. Yeah, so this is Linux running in Windows here. Obviously, I don't really use it to be honest. I've used Linux many times in my life, but yeah, so there's Linux running in a virtual machine. I could run Windows in a virtual machine. I could even install a virtual machine inside this virtual machine and have some sort of virtual machine inside a virtual machine situation. But there you go. So that's basically what a virtual machine is. I can run multiple of these, as many as I want really. And obviously, running a virtual machine, you're sharing resources. So, I'm sharing resources between, between my computer and this, because obviously, this is taking up some of my processing power, and quite a lot, because obviously VMware is going to be quite a beastie thing, but I do have quite a reasonably good computer, so I'm fine. But there you go. Yeah, so that's basically it. That's what a virtual machine is. There you go.